Alright, I think figured it out. Okay, so I drew up my circuit down here again. This is just the same as this here again, only this time I used 10K instead of 22K. We'll see it doesn't really matter that much in the maths. Okay, so given voltage of the feedback is 1.23 volts, I show that here on the circuit. Linear output voltage, I'm just saying a constant 10 volts. So I have 10 volts right here. Beta, I found from the datasheet for the BC 327 to be 250 to 630. I use 250. You can go back and do all the calculations for 630. Doesn't matter. I don't really care that much. Find, I'm looking for the offset voltage. My assumptions, IES, which is given in this, what is that called? The Shockley equation. Look it up again. Shockley. The Shockley equation, which is this guy right here. Basically, it's just the diode equation, I guess. So I'm told this IES right here, I'm assuming is 10 to the negative 12. I could not find saturation current in any data sheet that I looked at. I have no idea. I did find like a negative 2 nanoamps, but negative didn't really make a whole lot of sense, so I suppose I could just use 2 nanoamps, but whatever. I really don't know, man. I'm assuming 10 to the negative 12. And I think that the math works out just fine. VT, which is the thermal voltage coefficient thing, I'm just going to assume 0.026 volts. So 26 millivolts. So yeah, my assumptions given, etc., everything inside of here is the solution. So here's my diagram again. Same thing, sorry, my pencil got dull. So here's the three equations right here that I use. So IC is equal to beta times IB. So IC is known. Feedback voltage, remember, we know that the current coming out of here so the current going through this resistor right here, we know that, and that's going to be 0.000123 amps. We know that from Ohm's law. So then from IB, we use this equation to get IB, and for that, so this is the base current, and that's going out that way, using conventional current, not whatever the other one is, electron theory or whatever. That's going to be 0.000000492 amps. And that is why I don't think it really matters what voltage or what resistor used, because that's a really small number. And the voltage gain across that is like 0.00492. We'll see that later. Anyways, that's the base current. So the base current coming out of here. To find IE, we use Kirchhoff's current law, so current in has to equal current out. So we add them up, we get 0.00023.492. So that's just this number plus this number. So that's IE. So now we know all of the currents going through this BJT. Now we can use this IE, this Shockley equation here to find our base to emitter voltage. So I just plug these numbers in into the equation. I use my calculator to solve it. I'm not going to go through it here. You know, I got a TI-89. Got to use it. You know, easiest way. I could go through and solve it, but whatever. I got negative 0.48432 volts. I keep all my decimals until the end, and then I even kept them in the end. Whatever. So that's my base emitter voltage. So now again, we assumed 10 volts right here. I calculated, because we're going this way, that means that this point will have a higher current than this point. So then the voltage gain across this is 0.00492 because we had a current flowing through a resistor, V equals IR, Ohm's law. So that then I got at this point at the BJT 10.00492 volts. This is, I think it's forward biased. And so we basically subtract this guy here. That's still a little bit unknown, but anyways, once we subtract that, we get 10.4892 volts. Remember, this is a 10K, so we get another, this is a 10K resistor from here, so there's going to be a voltage drop to here to get up to here. So we add that as well. So from 10.492, we add 1.23-ish volts. We could add the 492 in the end. I don't think I do. So we could add, then we add 1.23 volts to this, and we get 11.7192 volts. Whew. I think, yes, IE will be a constant because, well, I guess, yeah, IC is constant, right? Because this feedback is, it's in our given feedback, 1.23 volts. It's constant because the LM2576 is going to do whatever it takes to maintain that. It will change this voltage to whatever we need that feedback to get that to 1.23 volts. I believe it's 1.23. We looked at the data sheet the other day. 1.23 volts. Yes. So, yeah, that thing's going to do whatever it needs to in order to get 1.23 volts on the feedback. So, this will be a constant current, and that means that our voltage, base emitter voltage, will also be constant. This shouldn't change with output voltages. So, no matter what, this guy here, yeah, this guy here should be the same. Nowhere in here do we take in to account any voltages other than across the resistors and the base emitter voltage. All that stuff should be constant. So we should have, this should be a constant gain here of 1.72, whatever. In real life, it's going to be different because this beta is, you know, we're assuming the whatever in IES, I don't know. But anyways, I think that's pretty much what I saw. It was around, it might have been more like 2 volts-ish. But I think this is the math behind it. Anyways, this is constant, which means that this is going to be constant. And they're going to be about the same as long as these resistors are the same. If you wanted a higher, voltage difference, offset voltage, just up this resistor up here. Make it a little bit bigger. Whew, okay, I can sleep now. Thanks, I'll catch you later.